and start the actually, I'll start from that slide, I think. I'll let the slide come up. First, any questions from anything we've covered so far?
Nope.
All right. We got this thing now. I believe we just had gotten started on example 3, but we ran out of time. So let's do a quick review on what we mean first by an autonomous differential equation. Remember what that means?
Autonomous means not bound by a parameter.
Okay, almost got it. Here's an example. This is the one we're going to be working on. dp dt, okay, p being the dependent variable, t being the independent variable, okay, that's equal to p times a minus bp, okay. Now what do you notice doesn't show up on the right hand side? That's the T.
Oh, I see. D.
Yeah, right. The T doesn't show up. In other words, the independent variable is nowhere to be found. It's just that you've taken the derivative with respect to that, but that derivative is strictly a function of the dependent variable. The independent variable doesn't show up on the right. That's an autonomous.
This very extreme angle that looks like
it does from here too, unfortunately. Sorry. The writing. Well, have you ever signed out?
On that screen that's moving, you know.
What's that?
It's hard to write on the screen that's moving.
Yes,
like
the screen moves, it's ionizing pen, all these things, yeah. But anyway, that's our autonomous equation, okay? Differential equation. Now, in looking at that, it's, let's see, A and B are positive constants, they tell us, okay? And it has what they call, and we talked about this last time, a normal form of dp dt is some function of p, okay? So in other words, the right-hand side is a function only of the dependent variable on the left-hand side. No dependence on the independent variable at all on the dependent variable. Okay. Now, when we look at this, one of the first things that we might notice is where is this derivative 0? Because derivatives of zeros mean you're going to have flat tangent lines. Okay? And those would be nice things to know. Well, what is true about a flat tangent line? Right.
At that point, the slope of the line is 0.
Exactly. And what is the slope?
The rate of change.
Yeah, the first derivative.
Oh, yeah. Tangent line of the tangent of the curve is the first derivative. Yeah.
Okay. And when the first derivative is equal to 0, dp dt is equal to 0, that means the right-hand side is equal to 0. And where is that true? And remember, this is the t variable here, the p variable here. Okay? And when that's equal to 0, what can you tell me about p's? Either.
I should.
Well, this is factored, right?
Yeah.
So either if product of two numbers is equal to 0.
Oh, yeah. It's in there somewhere.
Okay.
I cannot remember it right now.
Okay, but just look. If the product of two entities, that times that is equal to 0.
Right.
What does that tell you about one of those two? Or both of them?
So one of them must be 0.
Adds the b. The only way you can multiply anything by anything else and get 0 as an answer, one of those two things better be 0.
Right.
So either
If
p is equal to 0, or
p is 0,
or a minus
or a minus b.
bp is 0. And what would make that true?
If either p is 0 inside there, or if a and b are equal.
Not quite. A and BP are equal. In other words, A is equal to BP. That's
Right.
true, right?
Yeah.
And how about P then? How do you solve for P?
Well, let me remember.
Solve for P. Yeah, divide both sides by B. So either P is equal to 0 or P is equal to A over B. Now they already told us that A and B were positive. So B can't be 0, okay? Because they said A and B are positive.
So, okay, so positive and negative immediately is non-zero terms, right?
Say that
It's
again.
either defined as positive or negative, it's immediately a non-zero.
Yes, exactly. If it said A or B were non-zero, non-negative, then it could be 0, okay? Or not positive, it could be 0. But it says that A and B are positive or negative, it means it can't be 0, okay? Because 0 is neither positive or negative.
Well, by that definition, P would have nothing divided by some two numbers that are something can equal 0.
So what we have here is then, where the first derivative is 0, we used to call that our critical values, okay? That could be our maximum end or whatever, okay? Well, P equals 0, if this is the P-axis, that's your horizontal axis, where P is 0. There you know you have all horizontal slopes, 0 slope, okay? And A over B, I'm just going to pick a value up here to be A over B. So this will be A over B. I don't know what the relative sizes of those are, it's just that's A over B. So these are your two critical values, okay? Now, and the only two, by the way. So that means the P function is either increasing here or it's decreasing here. It can't ever be 0 again because those are the only two critical values.
Right.
Okay? And up here it's either decreasing or increasing, and up here it's either decreasing or increasing. We just don't know which until we do some test points. Okay? If we have enough information to do that. Okay? Now, all right. It seems like they are making some assumptions here that I can't quite see why they're making them. They say that between 0 and A over B, it has to be increasing. I don't know why they're saying that. Critical points equation. So the equilibrium solutions are those. By putting the critical points on a vertical line, we divide the line, blah, 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 we got that. The arrows on the line, figure 2.15, indicate the algebraic sign of alpha p is that on these intervals, and whether a non-constant solution is increasing or decreasing. I guess they just pulled them out of the air. I can't tell where they got them.
Which page are we on?
On page 40, example 3. I guess with B being positive, P being positive here, and because A and B are both positive, so A and B has to be positive. So it's something greater than that. But it still doesn't guarantee. It guarantees that P got to be positive here, but it doesn't guarantee that A minus BP does, because the relative sizes of A and B could be such that BP is greater than A, and that would make this negative, so the product would be negative, so your derivative would be negative in between there. So I don't know, they just, I guess, arbitrarily chose one, and they chose it to be positive there. Now, I don't know why, but they did, okay? Now, if that were the case, then at A over B, at that point, it reverses and becomes 0. On the other side, I guess that then has to be negative, because P is still positive, and if A over B were positive here, then it must go negative up there, because it goes, the slope of this goes to 0 there, but it could be an inflection point. I'm puzzled by why they put the arrows where they did. But it's okay. I mean, they just did a representation like this side rather than doing this side. Okay? Now, I don't think it's worth wasting time over. Because down here, P has to be negative, and A and B are both positive, but still, if A was less than BP, then that would still be, so I don't know. We'll just choose those three just like they did. They arbitrarily chose them. They indicate the algebraic sign on those intervals, whether a non-constant solution is increasing, decreasing on the interval. Okay? Okay. Don't know. Okay. So that figure that you see in the text there is called a one-dimensional phase portrait, or simply the phase portrait of the differential equation. The vertical line is called a phase line, and it just gives you the relative directions. Again, I can't see that he gave you enough in the problem to know whether the arrows are up or down. But whatever you choose one to be, then the others are pretty much fixed. Okay. Now, the next figure shows the two critical points there, which are obviously different from this one. They show it's going down in the center one. And again, there's no real reason, but they're just showing possible values of solution curves. Okay. And these are regions. The region we have here, the region P greater than A over B, P between 0 and A over B, and P less than 0. Okay, those are the regions here. The one they show here, regions 1, 2, and 3. Okay, where your C1 and C2, your two critical values for your y variable. Those are where the derivatives are 0. Okay. But in between, they have to be strictly monotonic. Okay. All right. So let's go back to this example we were just doing, example 3 revisited. The three intervals determined on the p-axis and phase line by the critical points 0 and A over B now correspond in the TP plane, that's as opposed to XY plane, to the three subregions, and here they actually give you potential values. Okay, up here the slope of that curve is 0, so you have a horizontal asymptote here, and it's going down and crossing at some point. They call this P0. Okay? And wherever it goes from there, we can't tell. Okay? They said it was increasing here, so we're going to choose that it crosses there at t equals 0 at another P0. In other words, I don't know why they're naming them all the same thing, but they're saying this is a S-type curve approaching P equals 0 as it goes to negative infinity, t goes to negative infinity, approaching A over B as a horizontal asymptote, where when t is going to positive infinity. And then similarly, and they just pick some point, another P0. It seems like they name them differently, and it's going on like that. So this is just sort of an arbitrary picking of places here. This phase portrait tells us P is decreasing in R1. Okay, R1 is the one down here. This is R2, and this is R3. That's just region 1, region 2, and region 3. Okay.
See the original equation where its first derivative, the graph of its first derivative looks like this.
What's that now?
I kind of want to see the original equation.
Yeah, well, they never gave us one. Right. I mean, they just said P, yeah.
Well, I want to see the original equation whose first derivative looks like this.
Right, exactly. And that's, yeah, that's what you're sort of backing into.
Yeah. Because it seems to, at first glance, it seems to violate, or the autonomous side of it seems to be like a workaround of the old rule that you couldn't have two independent variables occupying the same dependent variable.
Right.
And then this is, because there's theoretically no correlation between our, well, t is the horizontal axis, but it isn't the dependent variable.
Right. Yeah. Well, part of that is, okay, think of this in terms of initial value problem. If your initial value for t equal whatever the p was negative, then you can't be up there. Okay. You have to be in this. So this is
like possible outcomes. Given.
Right. And that may be why they use the same P0 there, because they can't coexist at the same time. Either your P0 is there, or it's there, or it's there.
Yeah.
And depending on where it is, with this function, it's going to do like this.
Kind of the sensitive dependence on initial conditions, a little chaos there.
Right. Yeah. That can be. Yeah. It's wherever you start, and this is where t equals 0. P is, if it's negative, you got to be down here. If it's between 0 and a over b, you got to be in that range.
Right.
If you're greater than a over b, you're going to be up there somewhere. Okay. And there are functions, but it depends on where you're. And in a sense, I guess it's autonomous, and it doesn't depend on t. It depends on p. You know.
Right.
Whereas usually
so
you
I
think
want to see how t loses or no longer becomes the dependent variable.
Yeah.
Sorry, the independent variable. Yeah. Because usually t is the independent variable.
No, usually time is the independent.
Right.
Okay.
So I want to see what equations where the first derivative, the time is no longer the independent. That would be interesting to see.
Yeah. All right, Dan's here. Good deal. We just did examples 3 and 4. Then we basically, I think, beat them to death. So we're just about to move on to example 5. Okay? And this is reflecting back on what we did last time. we were just started talking about autonomous differential equations. Okay, and here's another one. This autonomous differential is dy dx, going back to our familiar y's and x's. Last two examples are p's and t. Oops, I say x and I write t. Okay, something's a little wrong in the upstairs. Okay, dy dx is equal to y minus 1 squared. Okay, now again, and I should have said this on the last one too. These are autonomous differential equations. What makes it autonomous is that your independent variable, the x, from your dy dx, y is dependent on x. That's what dy dx indicates. You always put dependent, y is a function of x, in dy dx, okay? But nothing depends on x. The derivative doesn't depend on x. Derivative only depends on y, okay? And many of our examples we did at the 1.3 were this type. The last one was sort of like this too. And this is what makes an autonomous differential equation. Now, both the last one and this one obviously are non-linear equations, okay? Because you have y squared, and you can't have that in a linear equation. So these are non-linear equations, and I don't want to say all autonomous equations, differential equations are, but at least these two samples were. Okay, so one of the things that we have to do here is pick out basically our critical values. And you go back to Cal 1 basically. What were your critical values? Where your first derivatives were equal to 0. Or where they didn't exist, but we're not doing that yet. Just doing where they're 0. Well, where is this one equal to 0? If dy dx is 0, that means y minus 1 has to be 0, right? Now, if y minus 1 is 0, then what's your critical value? Y would have to be, and now we're doing this, going back to this being y and this being x. Where was y is equal? Where is your derivative equal to 0? If this is 0, then this would be 0. And what value for y would that be?
1.
1. Okay. So let's put our 1 right here, or right here maybe. So that'd be 1, and this is 2. Okay. And this will be -1, and this will be -2. We don't need them, but I'm just writing them in. Okay. So therefore, here's your critical value. So nowhere where y is 1, everywhere where y is 1, your slope is going to be 0. No matter what x value, when y is 1, your slope is going to be 0. Okay. So, now this one I can tell you. This slope is never what? Negative, because it's a square. This one we know. So here the slope is positive, and here the slope is positive. So the function, y as a function of x, is increasing both above and below this line. Okay? Now, frankly, this one you only have two regions, region 1 and region 2. Or did they number them backwards? I don't know. It doesn't matter. But they're increasing both above and below. Okay? They're not naming the regions now, I guess. Okay? Now, if the slope here is 0 and this is strictly increasing, let's just say it crosses there. They usually call that a y0. If you know at t equals 0, that's your initial condition, your function must be doing something like that. Now, this is arbitrary. It may be a very gradual slope, it may be a very steep slope, but back here it's gradual because it's approaching 0. Okay. Now, if your initial condition here is, say, that one, they don't, well, they pick one below that. They pick one down here. Okay, that'll be fine too. Then it could be doing anything down here because it's an increasing function. It can't be up here. That would be decreasing. So it would have to be going here and then increasing like that. Okay, or something of that order. Okay, so you wind up with this type of a shape here, except they threw in something else here, and let me see why they say what they do. Single critical point at 1, we got that. Phase portrait there, we got that. Increasing function anytime it's less than 1, decreasing function anytime the value of y is greater than 1. Okay? And x is good for all minus infinity to infinity. Okay. Here they say for initial condition y of 0 equal to y0, and this is less than 1. So this is your initial condition here. This is your y0. Okay, now this one only has 1. The previous example had 3 different possibilities for the 3 different initial conditions. P0, P0, P0. They couldn't all be true at once. Only one of those is true. This one only has 1, and this your y of y0 is less than 1. Okay? And it has to be increasing. Okay? Now, I'll try to see where they get the other. Here's where we got it. See, they didn't do this on the last one, and that's what you kept saying. I wish could see the function p. Well, they never told us the function p. This one they do. The y of x, they give us is 1 over, I can't write. Okay, let's get it right this time. Okay, 1 minus 1 over x plus 1/2. Okay. Says, oh, no, can't read. X plus c. Okay. I know I saw 1/2 somewhere, but it was not there.
It's further down.
Further down. There it is. Okay. 1 minus 1 over x plus c. See, the thing that I found really irritating about this is I'd love to have my book on this side because I'm left-handed, so I could read the book and write, but because of the setup here, I can't possibly get it there because my cord has to be here. It's not long enough yet. So I'm stuck having to do this all the time, so I get lost to where I am in the book. So there we are. There is your 1-parameter family of solutions for this differential equation. Okay? Now, I don't recall that we've done that one before, but we could go back and verify that is a solution. They said see problem 4 in exercise set 2.2. Thank you very much. We haven't gotten there yet, so that's why we haven't seen it. Okay, but they're giving it to us. Now, with that in the picture here, okay, for initial condition, y0 being less than 1, that puts us down here, so we're not up there. So I really, let's go on and delete this. We're not up there because our y0 is not there. We're down here. Okay. A given initial condition determines the value for C. They don't tell us what it is. Oh, yes, they do. For the initial condition, say y of 0. Let me find my pen again. Y of 0 is equal to -1, and that's certainly less than 1, so we're in the right area here. So that would be 1 minus 1 over 0 plus c, because x is 0 and y is minus 1. Okay? So what I'm going to do is, this is a little weird looking, -1 is equal to 1 minus 1 over c. So what I'm going to do is subtract 1 from both sides. and that gives us minus 1 over c is equal to minus 2. Multiply both sides by 1, then reciprocate, c is equal to 1/2. Okay, so if c is equal to 1/2, then going back here, this will be 1 minus 1 over x plus 1/2. Now we know immediately what value x can never be. What is it? Negative 1/2. Okay. Now I did my scale here, 3 blocks to 1, so that's a 1. This is 2. This is negative 1, and this is negative 2. Okay. So I came pretty close to doing it. Negative 1/2. This is x can't equal negative 1/2. There it is. So I'm not too far off. Got a little bit carried away here. That's a vertical asymptote. In fact, sometimes vertical asymptotes I like to put red, meaning don't touch it. Don't get close to it. You know, well, you can get close, but don't touch. Okay. Yes, actually you can. So we have a horizontal asymptote at 1. I'll go on, well, I already changed my red, didn't I? I'll go on and put that 1, you know, I thought I went to red. Okay. We'll put the horizontal asymptote as red also. Y is equal to 1. And we'll leave and the vertical asymptote I always like to have red, just for general. So this is the curve we're on then. You know, oh no, we don't show that either. We know that y of 0 is negative 1. So that changes my curve here to, oh, my eraser's not working. Okay. There it goes. Okay. So they just told us this one, that y of 0 is negative 1. So when x is 0, y is negative 1. So that's where we're starting from. So the curve does something like this. Has to pass through the initial condition, has to be approaching negative 1/2 on the vertical asymptote, and has to be and it always is increasing. Okay, and you got that from the fact that this thing's always positive. So we put together everything we need here. Okay. Now, what if we had a different initial condition? Do you want to do this in a different color? What color would you like? Blue. Light or dark? Dark. Okay. We'll do dark blue here. Okay. What if we had y of 0 is equal to 2? Your initial condition is 2. Well, that means when x is 0, y is 2, there we are right up here. There's your initial condition. Wrong. Oh, okay. Yeah, okay. Okay. Now we go back to our equation again, and this is equal to 1 minus 1 over x plus c. You're going to have a different c here, okay? You can't have the same c. You can't have that negative 1/2 there. Won't work there, okay? In fact, let's go on and fill in this one, because I'm going to have to do some erasing here. If you're, obviously, if you drew this curve completely, you would have a curve up here too. But it never can happen. Not with this being our initial condition. You're never going to make it up there. You can't, it just won't happen. However, when you have that as your initial condition, everything has to be changed, okay? You'll have a different vertical asymptote. Your horizontal asymptote will stay the same. So not everything changes. But your initial condition changes, and your curve location changes. Okay? So let's go on and erase what we have here. The function just will not go here, not with an initial condition. Okay? The slope's right and everything else is right, but not with an initial condition t equals 0. T is never equals 0 here. Okay, so all right, so now we're going to erase this part because that was this graph, and we'll erase our C calculations because it's don't change. If I can get the pen to erase. Okay, we'll change our vertical asymptote, and this function will of course change, and that will no longer be our y sub 0. There's our y sub 0, and this part will change. Okay, I think we're done with the changes now. So let's see what things change to. Am I still blue? I don't think so. Get back to blue. Okay, yeah, because I changed to do the other part. So when x equals 0, then of course that will be 0, and you have 2 is equal to 1 minus 1 over c. Subtract 1 from both sides, and that becomes 1 is equal 1 equal negative 1 over c. So c is equal to negative 1. Oops, I didn't get enough erased, did I? Okay. Something wrong with this picture here. Yeah, no, that's right. Yeah, c is equal to negative 1. We got it. So now our equation, I wish I'd kept it written. I didn't. I'll write it again. Y is equal to 1 minus 1 over x minus 1. Your c is negative 1. So here where your vertical asymptote going to be. Nope. Your denominator can't be 0. That's x minus 1 can't be 0. X minus 1 can't. Okay, yeah. So that makes your, let me go back to red to do our vertical asymptotes again. Our vertical asymptote, well, I thought I went back to red. There we go. Vertical asymptote becomes 1. Okay? So now we're in this portion of the curve. Okay? Blue again. Oops, I did light blue. I want dark blue. Okay. Now we must be over here. Okay? The part we couldn't get to before because it wouldn't fit our initial condition. Now our initial condition there. Still the horizontal asymptote has to be at 1 because of this. Y minus 1 equals 0. So that's where it's approaching. But the vertical asymptote, and it has to be increasing everywhere because the slope's always positive. So now it's approaching the vertical asymptote from there. Because we know that the y, when you plug in, well, they told us y of 0 was 2. So that fixes us at that point. So now we must have a curve that goes through approaching x equal 1 but never touching it. Okay. Now, I just did approximate curves, but you could, I don't want to try to get any more precise than that. Okay. So you plug in, you go back, you know, it's sort of a dancing game here that you use the pieces of information you get, one for the whole function and one for your initial condition, and the fact they told you that was a function that fit it. We didn't verify that, but they say you'll do it in section 2.2. So we'll get back there later. All right. let's see. Okay. All right. I'm sure there's some insight in there that I'm probably missing, but that, to me, was just giving us two samples and how initial conditions can completely change which portion of a graph you're looking at and lots of other things with it. And by the way, this had a portion that you can't exist somewhere down here, okay? Vertical asymptote still there, horizontal asymptote still there, but with that initial condition you can't do it because x is never equal to 0 for this part. So,
if those curves can't exist, where are they given?
well, they're just showing that this function here graphs as that, but depending on what your C value is, well, your initial condition, one of them can happen and one can't happen. Okay. In the earlier one, they gave us 3 different curves. Depending on where your initial condition was, you'd be on one of those 3 curves, but you can't be on all 3. You're only going to be on one. And it had 3 regions. One was down here, one here. So if your initial condition was here, you're on the curve down here. Initial condition here, you're on some curve up here. And it's pretty nebulous. It's sort of, without giving you too much information, it's saying this is how it's going to act. But given that initial condition, you can only be there. You can't be down here. They just drew it in to show this does have 2 pieces to it. These are hyperbolas, by the way. That's the one that fits the initial condition. That will not. That's the only thing I can see. Okay. Now, they give some names here, terms here, attractors and repellers. And they talk about it here, and I don't think they ever bring it up again. But since they talk about it, let's at least kind of get the gist of what they're doing. Okay, I'm going to erase all this because none of this, well, let's see. They're not using the same function, but they are using the same horizontal asymptote, so maybe we'll keep it. Maybe we'll just erase the pieces we don't want. Okay? So we don't want this anymore. I take it. I'll be very disappointed if we do. Okay. Whoa! All right. I guess I'll stay with the eraser. Clean up the whole works here. Oh, we could have left that one. Okay, I'll get rid of this. Just sort of almost get a clean slate for all practical purposes. Oops. Surprised I didn't lose my horizontal line there. Oh no, it was already there. It's fixed. Okay. I'll go back in and call that region 1 and region 2 again. And I may go back to dark color to boot. Okay. Now, suppose that y of x is a non-constant solution to autonomous differential equation given in 1. Now, that was way back several pages ago. Way pages ago. Very first of the chapter. dy dx equal f of xy, but they said it's autonomous, so it wouldn't have a x dependence here. Non-constant solution of the autonomous differential equation given in 1. That C is a critical point of the differential equation. So they're calling C's your, yeah, okay, that's okay. Critical point. There are basically 3 types of behavior that y can exhibit near C. Okay, now we've labeled the C as 1 here again. Okay, horizontal asymptote, horizontal slope for your curve there. Okay. Now, when both arrowheads on either side of the dot labeled C point towards C, we got this one pointing towards C. This is our C is equal to 1 here. If this one's also pointing to C, okay, then we call C, guess what, an attractor, okay? And that would mean it's not the one they show here. They show it repelling here. All right, okay. This would be the attractor state, okay? The second one here would be the repeller state, okay? That's if your arrows were going in the opposite direction, away from C. Whoops. Okay. There and there, that would be a repellent state. Now, you got two other possibilities. The first of these is going toward and away, like that. Above you're going away, below you're going toward. Or the last state would be exactly the reverse of that, that you're above you're going toward, but below you're going away. Okay. So those are the four possibilities. Both going toward, both going away, up and up, or down and down. Okay. Four possibilities. Okay. When they both are going toward, let's see, I got to get the right thing here. When both arrowheads on either side of the dot labeled C point towards C, okay, all the solutions that start from an initial point x0 or y0 sufficiently near C exhibit asymptotic behavior that the limit as x approaches infinity or y of x is C. For this reason, the critical point C is said to be asymptotically stable, and using a physical analogy, the solution that starts near C is like a charged particle that over time is drawn to another particle, to a particle of opposite charge, and so C is referred to as an attractor. Okay.
This is basically the same equations governing Coulomb's law.
What's that?
It's basically the same equations that governs Coulomb's law.
Yeah, exactly. And then an attractor. Okay. If both arrowheads on either side point away, we said the critical point is said to be unstable, and the critical point is also called a repeller because the points are going away. Both of them would be pointing away. The upper one away to up and the lower one down, away from that. The other two, this one and the one where they're both going up, are called unstable. Okay? An unstable critical point, semi-stable. Unstable is when they're both going away. Semi-stable is when they're both going in the same direction, so one's going toward the critical point, one's going away. Now, what the advantage of all that is, I don't know. Maybe in some other course you'll run into that. Right now, I'm not really all that concerned with it. But let's look at the next. It's not really an example, but the thing they show in figure 21.1.10. This will be, this time, in addition just to, because this is where your first derivative is 0, I'm going to actually put it in like we did before. Your slopes here have to be 0, okay? So I'm going to put your slope of 0, okay, like they did. And that's at y is equal to 1. This is the one I was looking at before. Now let's look at some of the other slopes, okay? And I think you'll see, and I think they do these in light blue, so I'll do them in light blue. Okay, these, they all show slightly pointed upward. okay? And they look to be about the same amount of slope. I don't know if I'm reading that right or not, okay? And then as you get further away, they go steeper and steeper, okay? Okay. But on the lower side, they're also pointing away. So this would be one of those unstable states. This would be a repeller state because the slopes are going away in both directions. Okay? And ultimately they get basically almost vertical down here. Okay? With gradual sloping like that. Now, the one that they've drawn here, if I'm reading it right, is dy dx is equal to 2 over y minus 1. Okay, so obviously y minus 1 is an asymptote here, or y equal 1 is an asymptote, and they both, everything seems to be going away from that.
So where did you get that?
Second,
Where did you find that?
that's, you see in the center of page 43, the autonomous differential equation and direction fields, okay, like the third line from the bottom of that paragraph is that one, okay. And that certainly would have an asymptote at minus 1, at y is equal to 1. Okay. All right, now we go to yet another one. And, I mean, they just sort of hit on these, talk about them a little bit, and move on to something else. And so far have not been able to figure out too logical of a sequence here. But, I mean, they talk about things. So let's do another. What if we had something like this? I'm going to go back to black, I think, here. Y is equal to some function of x minus k. Okay, I don't know why, where k is some constant. And it's the graph of y is equal to f of x, rigidly translated or shifted horizontally by some amount k. So you also had a y is equal to f of x. Goodness gracious, this thing is driving me nuts. Okay, just won't write. Okay, it's just a translation. So if the first function was, and they show here y is equal to 0 as a critical point, and y is equal to 3 as a critical point. I better do it right here. Okay, so y is equal to 3 is also a critical point. Okay, now if your first function was this, arbitrarily that, and your next one was f of x minus k, that would just translate it k units from here to here. That would be your k units. Because remember, anything, when you're dealing with x, if there's a minus sign, it's to the right, and if there's a plus sign, it's to the left. X things are always backward. Okay? So that would be k units to the right. If you're, I probably should have done different colors. If this was that one, then this would be that one. Same function, same shape, it's just horizontal translation to the right, k units. Okay. Now, if, however, you were up here and your f of x was like this, and remember these are all pointing, at least for now, pointing in that direction, the one up here, then, and I probably should have done this one, they did it in red, so let me go and change this to red. If this was your f here, then you translate to the right k units, and it becomes here. So now this is your f, and this is your f of x minus k. F of x, f of x minus k. Or, and they did this one in green, so I'll try to follow suit. Down here, these curves are also pointing to the right. So anything coming off of, say, here, then that translation to the right would be here. So this would be your f of x, and this would be your f of x plus k. Now, they're parallel to each other, and why in the world they're doing very much with this, but these are your, again, as I talked about before, your three regions. And let me make sure I name them right. Yeah, they do. This is region 1, this is region 2, and this is region 3. If this was your, whatever your equation is, your function here, you'd have three possibilities. If your initial condition was down here somewhere, then you'd be with the green curve. No, not the green. Yeah, these green curves, not those. Okay. If they're in the middle part, you'd be with the black curves. If you're in region 3, you would be one of those red curves. Depending on where your initial condition was, that would determine both which region you're in, and then also the function would determine then which of the curves you would use. Okay. And again, I guess this has some really transitory meaning here that I'm not sure I know why they're spending all this much time with it. But here's what they say, red print. If y of x is a solution of an autonomous differential equation, dy dx is equal to some f of y, and boy did I ever, well, they messed it up. They said f of x. It can't be. If this is autonomous, that's f of y. Didn't even dawn on me now until, no, those are our solutions. So that could have been x. I'm sorry, that's right. Those were our solutions. They would have x's in them, okay? But your differential equation would be dy dx is equal to some function, and they shouldn't use the same f, but they do, f of y. The derivative is a function of y alone. The y is a function of x. X is still your independent variable, but your differential equation has no x dependence. The function has x dependence, but the differential equation does not. It's strictly a function of your dependent variable.
So because x has, the differential does not have x in it.
Yeah, the derivative does not have an x in it, right? Or your independent variable in it, right? What's that?
Y.
Second?
Then we're using a function
of y, and they shouldn't use the same name f for here and here, because those are different functions, but they did. And but this is your differential equation, and that's some, I would call it phi of y, and this would be some alpha. Your solutions for this differential equation could be any of these depending on what your c is. This would be one c, that would be a different c, that would be a c, that would be a different c, that would be another c and another c.
Now you're saying c versus k.
Well, the k is how much the shift is. Yeah, but that also, yeah, you're right. It influences the c. Depending on which constant you put in, because you see, all differential. I want to say all. The vast majority of differential equations will give you a family of curves. If it's first order, you have one parameter family. You always have a plus c somewhere in it, okay? Unless you know an initial condition, and then you use that solution with that one parameter, plugging in the place that you know, and that gives you the value for that parameter. So this could be c is equal to -3, and that c is equal to 7, or this would be they're going to produce a family of curves in the c. And in this case, that's related to the k. In fact, it'll shift it just so much. And whatever that function is, yeah, I guess the C and the K are the same thing in that case. Well, at least in the ones they showed it earlier, when it was x minus k or x plus k in your denominator. That would be the case. That would be your C. But they're showing this as a k in that position is going to do nothing but shift you. And that's your family of curves will then be horizontal shifts of each other. Okay. So let's go back to this. If y of x is a solution of an autonomous differential equation dy dx equal f of y, then y1 of x is equal to y of x minus k, k is a constant, is also a solution. Okay? In other words, if you have a solution, then a horizontal shift will still be that solution. Now, if you have an initial value, you determine which one that is. Okay? Let's see if we can find an example of that. Actually, these, no, they don't look at all like it. So let me go to a clean sheet here. All right. So we go again to dy dx is equal to some f of y. Autonomous differential equation. For some reason it doesn't write sometimes. Okay? Now, what if we know this one has an initial condition, y of 0 is equal to some y0. We don't know what value it is, but some fixed value. Okay? Then, y1 of x equal to y of x minus 1, x minus x0. Yeah, they called it k before, now they're giving it x0. Is a solution of the initial value problem that we just listed here. But in this case, I'm sorry, this is a new, same differential equation, but now we have that y of x0, a different initial condition, is equal to y0. So basically what it's saying is, it's sort of weird the way they're phrasing it. That would be one solution for that, if we knew that initial condition. But if you also knew that you had another y1 of k was just a horizontal translation, x0 units or k units, one way or another from that, then that same differential equation would now have a new initial condition to match that other line, this horizontal shift. And because you see, when x is equal to x0, then you have y0 as your answer. So, as before, that might be right here. Now it'll be over here. So the curves may be identical looking, but you've just shifted over. So that's a new solution for another, that differential equation if you had this initial condition. In other words, sort of like you were saying, the k does relate to the c's, because then you would have a different c. That would be your k here, and that possibly could be the new c. You just get a different family, a different curve in the family of curves.
Well, why would x at 0 minus x, why would that not be also classified as k? Because it's the same idea. They're both.
Yeah, and yeah, it's just
basically x0 minus x is a section on an interval.
Yeah.
And k is the exact same thing.
Right. Yeah. Exactly. And I think that's the circle they're coming to. They're saying that what you studied in pre-algebra, as a horizontal shift, now we're calling that some new value for x that shifts your differential equation solution from that initial condition to this one, that gives you a new shift, and that would be the same as if you had a different constant, in your family. Okay, that parameter, a different parameter, that should be. And that's also a solution for that differential equation. Woo, okay. This section left a lot to be desired in my mind, but any that are in the back of the book, try to do odds 1 or 3. And if they're in the back of the book, any of the odds 5 through 11. And if he's in the back of the book, 13. And try to do 15. 15 is more of an applied problem. An isocline is a line of equal elevation, as in on a topographic map. Okay, isocline. Isobar would be a line of equal barometric pressure, and isotherm would be a line of equal temperature. So iso means equal, so this would be a isocline elevation. Usually the discussion problems are not in the back, okay? But in 2.1.2, those are in 2.1.1, which we already did. 2.1.2, hopefully 19 will be back there. It may not be, but if it is, try to work through that. And then any of the odds 21 to 27 that may be in the back. Those are your autonomous first order differential equation. 2.1.1 was just direction fields. Okay? And I think that takes us down. Oh, and then try 29. 29, if it's back there, try to do that as well. Okay. Thank goodness we're finally getting to 2.2. How are we doing on time?
2 minutes.
It's time to go. So we'll start 2.2 next time. We actually get to solve some differential equations. I wish I could find a book that was like the one I had in college that just walked you through doing a differential equation. This has a chapter and 2 sections on La La Land. I don't care for it, but, well, 1 section, okay, 2 subsections of that. So anyway, there we are. Thank you, the 2 of you, for coming. I don't know where the rest of them are, but we will meet again Monday. I did give you your test last time, didn't I?
Yes.
Okay, good. And I think...
As far as I'm concerned, you can have it back.
Huh?
I said, as far as I'm concerned, you can have it back.
Finished, I take it?
No.
No, oh, okay. All right.